Yeah, thank you. Thank you, Jing, for the very kind introduction. Yeah, I want to first thank the EASF committee for organizing this webinar and for inviting me. I think this is a great platform, and I feel honored to give this talk today. So as Jing has introduced, my current work at the University of Michigan is focusing on surfaces and coatings. But today I would like to introduce to you my work, my thermal fluids side of my work, which was done at the Air Conditioning and the Refrigeration Center at the University of Illinois. So I will talk about liquid vapor phase separation as a way to improve the performance of microchannel condensers. So my PhD and the postdoc work at the University of Illinois revolved around the vapor compression refrigeration cycle. So in the center of this slide, we are seeing a typical vapor compression cycle, which comprises of a compressor, the condenser, the expansion valve, and the evaporator. So I believe we all see this cycle in our thermodynamics textbook. And this cycle is dominant in the refrigeration industry. It provides over 95% of the artificial cooling capacity in today's world. So we can find its application in our cars, in our commercial buildings, where the heating, ventilation, and air conditioning system consumes the most energy. And also at our homes, we all have refrigerators and air conditioners, and also for industrial applications. So because of this giant size of the industry, even if we just improve energy efficiency for this system a little bit, it can generate great energy saving and be beneficial to the sustainability of our planet. So specifically, the heat pump system has drawn a lot of attention recently with the rise of electrical vehicles nowadays. So the heat pump system and the refrigeration cycle, they are exactly the same cycle. It's the difference is that the functioning part for the refrigeration cycle is the evaporator, which absorbs the heat. While for the heat pump system, the functioning part is the condenser, which releases the heat. And the heat pump has the advantage of being able to draw heat from variable sustainable sources, and its energy efficiency is higher than 1. So its energy efficiency is defined as the heat transfer rate of the condenser divided by the compressor work. It is higher than 1, so that is why it is better than the traditional Joule heaters. So my work focuses on those two heat exchangers, specifically the condenser for the refrigeration cycle. And I'm studying the Macrochannel Condenser, which has emerged as a replacement of the conventional round tube fin heat exchanger. So here on the left of this slide, we are seeing a round tube fin heat exchanger. So basically, we can see the copper tube. They are in round shape. On the right, we see a microchannel heat exchanger. The tube is revised to a flat shape, and inside one tube, there's multiple microchannel ports, which has a hydraulic diameter on the order of 0.1 millimeter to 1 millimeter. And it has several advantages compared to the round tube fin heat exchanger, such as a larger heat transfer area, reduced refrigerant charge, and higher heat transfer coefficient. And to maintain a reasonable pressure drop, the microchannel heat exchanger normally has multiple parallel tubes, and they are connected together by a common header. So the header is basically a D-shaped or round-shaped cylinder, as we see in this graph. And people has modified the port size to enhance the in-tube heat transfer, and also for complete picture, I'm just showing the louver fin on the air side, and the louvers are designed to enhance the air side turbulence, and that also increase the air side heat transfer. So nowadays for macrochannel condensers, people usually adopt the multi-pass design. So before I go to the introduction for the multi-pass design, let me just show you two figures about the fundamentals for heat transfer and the pressure drop inside the macrochannel tube. So here on the left, we see the heat transfer coefficient as a function of the vapor quality. The vapor quality changes from 1 to 0 from left to the right. This is to simulate a condensation process. As we see, as the vapor quality goes down, meaning more and more condensate is generated, the heat transfer coefficient drop. And as the heat mass flux inside the tube increases, the flow inside is faster, so the heat transfer coefficient will be higher. And for the dPdZ, the pressure drop gradient around starting from a value of 0.9 for the vapor quality, it also decreases monotonically as a function of the vapor quality. So with these two fundamentals in mind, let's look at a typical macrochannel condenser for automotive air conditioning systems. So this is a 4-pass macrochannel condenser, and each pass means multiple parallel macrochannel tubes breathed together by the louver fins. So we name that as one pass, and we can see that for the heat transfer coefficient at the entrance after a short length of desuperheating, because we have superheated vapor going into the macrochannel condenser. As soon as the flow enters the two-phase zone, we will have a peak of the heat transfer coefficient, so which is shown here. And as the condensate is formed inside the tube, the quality decreases, so the HTC also decreases. And the increase at the entrance of each pass is because of the reduction of tube numbers in each pass. So with the with the fewer tubes in each pass, the mass flux become higher. So that's why there's an increase of the that's why there's an increase of the heat transfer coefficient. And for the pressure of the refrigerant inside the tube, it will decrease monotonically as a function of the dimensionless length. So this is indicating that the frictional pressure drop is dominant compared with the deceleration pressure increase. So with this in mind, here comes my PhD work concept, which is use separation to as a low-cost way to improve the condenser performance. So here in this slide, we are seeing here in this slide, we are seeing again a conventional condenser which has an inlet at the top and the exit at the bottom, and we see a similar heat transfer coefficient profile. That there's a peak at the entrance of the two-phase zone in the condenser, and the separation design simply move the inlet to the condenser to the middle of the height, and through the first pass after desuperheating and the condensation, we will have two-phase flow at the end of the exit of the first pass, entering the second header. And here, using only gravity, we expect more vapor to go up and more liquid to go down. If pure vapor goes into the second upper pass, basically we will recreate the onset of condensation because the vapor quality is equal to 1. So basically we will have this elevated thermal heat transfer profile in the upper pass. And at the same time, with the higher quality going up because of mass conservation, the quality going down will also be lower. So the heat transfer coefficient in the lower passes will be will be decreased, and we only talk about HTC or H in this equation. But for the total UA value for the heat changer, A is also an important parameter, which is the area. So if we allocate more tubes to the upper pass, which has a higher heat transfer coefficient, it will provide the potential to improve the condenser performance as a whole. So here in this case, we see that indeed with a perfect separation inside the second header, the separation condenser will have a higher condenser capacity, which is the QC. And the beauty of this design is that with using only gravity, there's almost no additional cost besides recircuitry at the manufacturing phase. And we have been assuming the separation is perfect in the last slide. And here in this slide, I'm comparing a perfect separation with a non-perfect separation. So here in the red curves denote the XU equal to 1, and the pink curves denote XU equal to 0.7. And we can see that as soon as the upward moving quality decreased, the HTC will also decrease, and we have some gain back at the same time on the lower pass. So here comes the heat transfer rate for these cases, and here the perfect separation outperforms the non-perfect separation. So what is the real XU? Apparently, it will affect the heat transfer inside the tube. So that is also one important question that I solved in my PhD work, and I will introduce that later. And so with this in mind, we've seen from modeling with a perfect phase separation, there's a potential to improve the condenser performance. And what I did first in my PhD work is to test two prototype, a separation condenser prototype in a real mobile air conditioning system, and see whether it can really bring some benefits to the air conditioning system. So in this typical air conditioning system with two chambers and a compressor in between, its cooling capacity is between 3 to 5 kilowatts. Condenser was the only part that had changed, and all the other parts remain the same. And here is the conventional condenser and the separation condenser that I compared. They have the same number of tubes, same number of fins. The only difference is the pass circuitry. One has the separation design and one is the conventional design. And we have conducted good measurement for our system. The measurement of uncertainty of the condenser heat transfer rate or the condenser capacity is within +1 - 1%, and the COP, the coefficient of performance, which is the characterization of the energy efficiency of the system, is within ±1.5%. And also we have acquired independently the air side and the refrigerant side capacity, and they match very well. So in this slide, I will introduce two kinds of experimental comparison to compare the two condensers. So on the heat changer level, I'm using the condensate flow rate as the comparison criterion. So basically, in this enthalpy difference equation, we control the inlet specific enthalpy and the outlet specific enthalpy for the condenser to be the same. And whichever one has a higher m dot, it will generate a higher QC. And from our experiment at two different SAE test conditions, basically they have different air speed. We can see that the separation condenser has up to 7.4% higher condensate flow rate compared to the conventional condenser. And after that, we also conducted a system level comparison, which used the COP as the comparison criterion. And we have seen for different testing conditions from 1.3 to from 1.3 to 6.6% improvement at the matched cooling capacity. And if we look at in detail what is happening, why there's such improvement, it is because with a higher performance condenser for this red cycle, which use the separation condenser, the saturation temperature of the condenser is lowered, so the exit enthalpy for the separations for the condenser is lowered. So at the same cooling capacity, the delta H on the evaporator side becomes bigger, so we don't need as high mass flow rate as the conventional system. So that will cause some reduction on the compressor speed because we don't need a higher mass flow rate. So that brought some extra benefit on the isentropic efficiency for the compressor, which is about 3%. But the source of the improvement came from a better condenser. So we attributed the 6.6% improvement to that. So with this promising experimental work, experimental validation for the separation condenser, we want to look further in the fundamentals in the header and study the two-phase separation inside the second header, because that is where the phase separation happens, and it will determine the downstream heat transfer performance. So that drove me to conduct experiment in another facility, which is a pump-powered cycle. In that cycle, I use electric heating to create a two-phase flow coming into the second header, and I made the header transparent to allow flow visualization. And the downstream of the header for the two exits, I use the separator tank to measure the liquid flow rate, and the mass flow rate meter to measure the to quantify the vapor flow rate. And from my test, I found that the separation in the second header is usually not perfect, and I have to define the vapor separation efficiency, which is the upward moving upward moving vapor flow rate divided by the total vapor flow rate coming in. And the liquid separation efficiency is defined as the downward moving liquid flow rate divided by the total liquid flow rate coming in. And these two separation efficiency are closely coupled. And I changed the openings of the downstream valve to simulate a different downstream flow resistance for the second header. So just to show you one example for the parametric study that we did, and this slide shows the effect of the inlet mass flux. We can see that from the left to the right at a constant inlet quality, as the mass flux coming in becomes higher and higher because more vapor is coming in because of the higher inlet mass flux. Those vapor will change direction when they hit the wall, and the more vapor will move upward with a higher inlet mass flux. And this higher upward vapor mass flow rate will be able to entrain more liquid upward. And once the liquid is entrained and exit through the upward exit plane, that will decrease the liquid separation efficiency, because the downward direction is the desired direction for the liquid. So with more liquid being entrained upward, the liquid separation efficiency will drop. So this our flow visualization basically confirmed our assumption here. We see that the liquid separation efficiency at L drops from 1 to 0.7. And if we look at the details, locally, what is happening, so we can see more interesting phenomenon. So basically, in this slide, also compare at the same time the nominal a small diameter header and a large diameter header, and the phenomenon is totally different. With this small diameter on the left, we can see that this liquid in the upper portion of the header is moving upward, while in the lower portion of the header, the liquid is moving down. Well, when we increase the header diameter, we can see that there's basically the waterfall phenomenon, just because the vapor velocity is not high enough due to the larger header diameter. It's not enough to entrain the liquid to go upward. So basically, in these two videos, even though it's taking at the same position of the header, all the liquid coming in will drop downward. So with the insights, this kind of insights of flow visualization, and together with the measurement of the separation efficiency, that that enabled us to build a 1D mechanics model to simulate the phase separation phenomenon inside. So if we think about the phase separation phenomenon, it can be a little bit complex, because it is not a single tube. It's not a tube that has a single mass flux or quality. It is actually a combination of 22 consecutive segments, because in my specific case, I have 21 inlet tubes. That's why 22 the number. And those consecutive segments, each of them will have a different mass flux and quality. So how to simulate this phenomenon it can be a little bit challenging, but our way is to calculate the local vapor velocity and using the local vapor velocity to calculate the drag force for the liquid coming in from each inlet tube. So basically, with a higher vapor velocity, the drag force will become higher. So a higher portion of the liquid will be entrained upward. And basically, we can derive this liquid split ratio for the liquid coming out of each inlet tube. And once we know how much liquid coming from one tube goes up, we can accumulate all the upward moving liquid flow rate and add them together. Then we will be able to calculate the liquid flow rate and the at the upward exit plane and the downward exit plane. Thus derive the final separation efficiency. So this model has been validated by our experimental results. And with this model, together with the flow visualization, we can explain more in details why the separation efficiency happens. So, so in this following slides, I'm going to show you several different a parametric study, which will include first the inlet mass flux and the header diameter. So here we are comparing for the same header when the inlet mass flux become doubled, that will essentially double the vapor velocity inside. And here this the red denotes the vapor superficial velocity, and the blue in each graph denote the liquid superficial velocity. With the almost doubled vapor superficial velocity, apparently more liquid is being entrained upward locally, so that that will get us a lower at L, the separation efficiency. And besides the higher vapor velocity, we will in our model we also need to determine the drag force. We also need to determine what's the shape, basically the size of the liquid droplets, and we use a flow optimization model to do that. And we see that with the higher inlet mass flux from the flow optimization model, the diameter of the liquid also becomes smaller. So that makes it even easier to be entrained upward. And another, the second parameter is a larger diameter. So when we compare these two curves, we need to compare the separation efficiency at the same vapor separation efficiency as I have introduced before, these two, they are closely coupled with each other. So with basically with the same portion of vapor going up, the larger diameter header has a higher liquid separation efficiency. So intuitively, it's like increase the header to a separation tank with a larger header diameter, the vapor velocity. Yeah, the last parameter we we study for different applications for the for heat pump and air conditioning cycles is different fluid properties. And here I'm comparing the from the high pressure R32 to low pressure R245 FA, and we can see that among these three different refrigerants, the 245 FA apparently has the lowest ETA, and that is because first it has the smallest droplet diameter, and as I have mentioned multiple times, with this smaller diameter, the entrainment criterion of the vapor velocity, which is the terminal velocity I use here, becomes lower. So it makes easier to entrain the liquid droplets. And at the same, on the other hand, when we compare the rho v, the vapor density for these three, the 245 FA has the lowest rho v, which will give the highest UV. So these two factors combined together results lowest ETA for 245 FA. And if we compare 32 and the 134A, they will have the same entrainment velocity criterion, but the vapor velocity for the 134A, as we can see in this row, is a little bit lower. So that means it's at the same inlet flow rate, the vapor velocity is a bit higher. So that will entrain more liquid upward. So compared to with 32, it has a lower ETA. So that concludes the parametric study of the second header. And besides this 1D modeling, I also conducted a little bit of a 3D CFD modeling, just to provide us more perspective and the details of the 3D flow field for this second header. And I used the commercial software ANSYS Fluent and used the Euler two-phase model to conduct the simulation. And here we can see that there's a similar location for liquid inside the on the tube wall compared to my flow visualization. And I'll skip the details due to time constraints. And here in this slide, I want to show the comparison between the CFD model and the 1D model, and how this CFD model actually helps me to conduct the 1D model. From the CME model, we can notice that there's a vapor vortices exist between adjacent macrochannel tubes. So essentially, those vortices makes the other half of the header, which is the right half of the header, the free flow region. So I use only this half of the header as the cross section area to calculate the vapor velocity, and use that vapor velocity to calculate the liquid entrainment in the 1D model. And at the same time, the CFD results also can give us the average, the mean velocity at each cross section of the header, and we can see a good match between the 1D model and the CFD model. And with a good match on the vapor velocity in red, we will have a good match of the liquid velocity. So essentially the liquid separation efficiency on the bulk will be the same from these two models. So that concludes the modeling for the second header. And with with this second header model being built, finally I can use this for engineering design and complete the modeling for the phase separation condenser. So when we look at the separation condenser for each pass of the condenser, at ACRC at University of Illinois, we have developed a mature 1D finite volume model, which basically discretize each macrochannel tube into consecutive segments and calculate the heat transfer and the pressure drop in each of the in each segment. And my second header model says here, basically you from the input from the first pass, the second header model will generate the inlet flow rate and quality to the second upper pass and the second lower pass. And for each downstream pass, still the pass model is being used. And since these two streams combine in this receiver, so the pressure ending in the receiver should be equal. So iteration will be needed to get these two pressures to be equal. So that is this is a basic logic to build this separation condenser model. And we have validate our model both on bulk and locally. So on bulk, here I'm showing an example of the comparison between the experimentally measured condenser capacity versus the model calculated condenser capacity at the same inlet condition. So we can see that they agree very well. And not only that, when we compare the infrared image with the local temperature for the condenser with the model prediction of the wall temperature, we can see that the temperature distribution also matched very well. And specifically, I want to point out that with the inlet quality to the second header being 0.6, the upward quality going into the second upper pass is equal to 0.7. So it's not 1. So this indicates that the separation in the second header is not perfect, but this higher vapor quality is enough to provide the benefits of phase separation. And if we look at all the test conditions, the upward quality XU is about 0.1 to 0.15 higher than the inlet quality. So finally, using this model, we can conduct a condenser optimization, and this can guide our engineer design for this novel low-cost condenser design. So we have enumerated 330 pass circuitries, and on top of that, to match the refrigerant side and the air side, I vary the fin density and the air velocity in the upper pass and the lower pass, and to see whether that can bring further improvement to the condenser. So here, this shows one example in which at the uniform air inlet velocity, I changed the upper fin density while maintain the total fin number to be the same. And we can see that as we decrease the fin pinch, which means increase the fin density in the upper pass. So this is like giving more heat transfer area to the upper pass, where the heat transfer coefficient on the refrigerant side is higher. So we can see that effectively increase the condenser capacity, and the highest is around here. And if we compare our optimal design with the after fin and air velocity optimization, we can see a further improvement of the condensate flow rate compared with the separation condenser prototype that I have shown from the experiments. So we have given some guidelines for how to arrange the tube number in each pass for the separation condenser, and our optimization results shows that the optimal condenser, which is the red here, it has almost 18% higher condensate flow rate than the conventional baseline, while the separation prototype which I tested in the experiments, has about 7.4%. So this is about like 2.5 times higher of the 2.5 times of the original improvement. And in a system model, that can be translated to a COP improvement of about 10%. And if we put into perspective of energy saving, that can save around $1.1 billion of gasoline annually just for the vehicles in the US. So that concludes the separation condenser design of this talk. And here, next I will go briefly about even simpler design that I did for my PhD period at the University of Illinois. So we are thinking still using the liquid separation concept, but we are thinking whether there's an even simpler way to achieve liquid separation. So basically, our design is creating an orifice hole in the header bubble for the second header, and let the liquid being extracted through the orifice hole and essentially bypass the second and the third passes and enter directly to the fourth pass. Because as I have introduced the liquid as already the phase we want for a condenser, and if we can give more vapor to the tube, that can reduce the liquid resistance from that can reduce the liquid thermal resistance and thus increase the total heat transfer. So this is also a design essentially with a very low manufacturing cost. And here in this graph, we are seeing the benefit on heat transfer coefficient, because the liquid is being here we assume a complete separation as a proof of concept, and as all liquid is being extracted through the orifice hole, pure vapor again comes into the second pass. So we see similarly as before a peak of the HTC. However, as because the mass flux is reduced due to only vapor, that can create some penalty downstream. So because of the lower mass flux downstream, the HTC will reduce downstream. And here this U has the U which incorporate the air-said heat transfer coefficient. It has the same profile and a similar profile. And but the benefit of under pressure is always there, because of reduction of mass flux in the second pass and the third pass. The pressure drop is smaller, and because of the smaller pressure drop, since it's in two-phase zone, the saturation temperature is also is effectively increased. So with the smaller pressure drop, the pressure becomes higher, and the higher pressure means higher temperature. So that increase actually the refrigerant to air temperature difference, which will increase the condenser capacity eventually. So in this case, we can see a dramatic reduction of the refrigerant side pressure drop, and we can see a trade-off between the HTC and the pressure drop in the condenser, and this is calling for optimization for the path circuitry. But in this work, I will just show you for a certain path circuitry whether there's really some improvement on the condenser based on our experimental results. So basically, I've been using this same condenser and create a bypass for the second and the third pass. This is to simulate the extraction hole in the baffle. So this bypass essentially it will recombine with the exit flow from the third pass and enter the fourth pass together. So in terms of the flow circuitry, it works the same as an extraction condenser. And the beauty of this design is that with these needle valves, we can simulate actually different hole size for the full extraction, and thus study different design. And the effect of extraction flow rate on the condenser performance. And I've quantified similarly the liquid separation efficiency and the vapor separation efficiency. And this shows more details how we conduct these experiments, basically to always ensure a perfect phase separation in the separator for the bypass tube, so that we can measure the vapor and the liquid flow rate. And when both valves are closed, essentially there will be no flow in the bypass, and the condenser will just work as a conventional condenser. So here I'm showing the effects of mass flux, and first effect of extraction mass flow rate on the condenser performance. And we can see that there's always an optimal extraction flow rate, which gives the lowest TCRO, the condenser refrigerant outlet temperature. So with this temperature to be lower, the exit specific enthalpy for the refrigerant is lower, so the condenser capacity is higher. And similarly for 25 gram per second on the for the total flow rate, also there's an optimal flow rate. And surprisingly, we can see that with a moderate subcooling for the condenser, the subcooling is defined as the difference between the saturation temperature at the exit and the real temperature of the refrigerant at the condenser exit. So when this subcooling for the condenser is moderate, we can see that the optimal extraction flow rate is always around 20% of the total flow rate. And however, the case will changes when we change the subcooling for the condenser. So again, on the upper half of the slide, when the subcooling is changed to is around 5 Kelvin, we can see that and the inlet mass inlet quality to the second header is correspondingly around 0.6. The optimal flow rate is about 20% of the total flow rate. But if the subcooling is 20K, which indicates the first pass has done a lot of the heat transfer already, indicate that means a higher effectiveness of the first pass. We can see the optimal flow rate is dramatically reduced. It is about 8% of the total mass flow rate. So this is also basically telling us a higher effectiveness of the first pass will require less liquid extraction. So then in the next, we also compare the condensator flow rate, which is as a comparison criterion, which is the same criterion I used for the separation condenser, and found up to 4.7% improvement. And also in this research, we have also studied different the effect of the effect of total flow rate on the separation phenomenon inside the second header. And we can see that with a higher inlet flow rate, that will turn the two-phase flow in the second header more. So make this flow state at entering the second pass and entering the orifice hole to be closer. And we can see that the quality for this at these two locations become closer compared to the 25 gram per second total flow rate case. And correspondingly, the 25 gram per second for the total flow rate will give us a higher liquid separation efficiency at the same vapor separation efficiency in the header. And finally, I'm going to show on the system level comparison, the coefficient of performance. We can see up to 5.2% of the improvement on the system coefficient of performance as we increase the extraction mass flow rate. So there's essentially there's an optimal extraction flow rate to give a a highest COP for the system. And again, we found a similar rationale for why the system efficiency is increased. That is because the better extraction condenser effectively lower the saturation temperature for the condenser and bringing some extra benefit on the isentropic efficiency of the compressor, reduce the compressor work at the same cooling capacity. So the COP of the system becomes 5.2% higher. So as a summary, for the separation condenser research, we have conducted first-time flow visualization and the measurement of the flow in the second header, and we will build first-time models for the phase separation phenomenon in the second header and the condenser. And our separation condenser experimental results showed 7.4% increase in condensate flow rate and 6.6% improvement in system COP, with the separation condenser being optimized using our condenser model. The improvement is further pushed, and for the extraction condenser, for in an unoptimized condenser geometry, we see a 4.7% improvement in condensate flow rate and about 5% improvement in the system COP. So with that, I want to express my immense appreciation for my PhD advisor, Professor Pega Hrnjak at the University of Illinois. And I want to thank my collaborators, Dr. Lili Feng, who was a former colleague in my group, and also Dr. Dandong Wang and Mr. Vladimir Mutin, who also worked with me for the extraction condenser project. And I'm grateful for the financial support from ACRC and the American Society of Heating, Refrigerating, and Air Conditioning engineers. So with that, I'd like to take questions.
Oh, thank you, Jun. Jin, you can go ahead to ask your question.
Oh, hi, Jun. Thank you for the talk. I think this is super exciting for me. So I have a question for your experiments. I think those are super awesome for those like condenser experiments. So first, I want to know what's the size for your experiments, and also I want to know, because you said you mentioned those velocity for the vapor and for the liquid. So because from those video or images, how do you measure those? Could you explain more about these details?
Okay, sure. For the condenser size, for your first question, yeah, this slide shows our condenser size. So this is on the order of magnitude of 10 centimeters. So this the width of the condenser is 70 centimeters, and the height is about 40 centimeters. So these are the real size of automotive Macrochannel condenser. You can actually find this behind your wind grill in your car. So today, yeah, if you're interested, if you look through the wind grill, like in the front of your car, look through it, you are gonna find a similar like a similar thing, just sitting right behind the wind grill. So we try to keep the scale as real as possible in our experimental system. Actually, all the components they are based on a real sized automobile reversible heat pump system. So yeah, that's about the size of my experiment. And for your second question, how I measure the vapor and the liquid velocity in my experiment, yeah, that's a great question. So yeah, so that's a little bit I didn't do a very detailed flow, like a video processing of the video processing derivation of the liquid velocity. Actually, this velocity of vapor, they are just derived based on the mass flow measurement from the mass flow meter in our experiment. Yeah.
So this capture the images because your setup is bigger than this, right? So this just a very thin layer near the edges. Is that correct?
Oh yes, yes. It's a thin layer of liquid on the near the edge. Exactly.
I see. And also, particularly because I'm at Wisconsin, so the winter is super cold. So have you considered like if in the very cold temperature, there also can be like those ice for the like for water. So how the solid state of the ice will affect this like a heat exchange?
Yeah, that's a great question. Thank you. Yeah, ice is a dramatic impact, has a dramatic improvement on heat changers. So once ice is formed on the heat changer, it works as a thermal insulation. And there's also a difference between frost and ice. Frost is much worse than ice if we like differentiate them. And the frost is so porous, it block a lot of the airflow. It also increase the pumping power for the air. And but just from the heat transfer point of view, ice basically works as a thermal insulation. And once ice is formed on the outdoor heat changer for like electrical for the heat pump for electric vehicles, that is a dramatic bottleneck. So there's a lot of work going on how to defrost outdoor heat changer for heat pump systems for electric vehicles. Yeah. Okay. So that it's a great bottleneck for in our area and for the heat pump studies.
Yeah, thanks for this answer. Thanks again for the speaking of the talk.
Yeah, thank you.
Any questions from other audience? I have a question actually, Jun. So the microchannels are in the order of like a few hundred microns, right?
Yes.
If we disregards the difficulties of fabricating smaller scale of channels, what is there any optimized predictions of channel size for these heat exchangers?
Yes. So I showed in my second slide. Yeah, there's a different studies on the port designs for microchannel tubes, and that's a great question. So I guess the port size is essentially determined by the tube major or the tube width of the microchannel, and how much the tube width is essentially determined by the application for our microchannel heat changer. So I would say that with my heat changer, the 70 centimeters wide and 40 centimeters high heat changer, so that's about this on the order of several hundred of microns. That is about the optimal size for the microchannels. But I know that, like for example, for electric cooling applications, those microchannels may be even smaller. So they may be on the order of magnitude of like tens of microns or just microns. I'm not exactly sure, but that is essentially determined by how much their microchannel tube is, if there's a microchannel tube, or if it's just a heat sink, then maybe just a bunch of microchannels. So for electrical heating, then basically the heat dissipation requirement is definitely lower. So maybe like I'm not exactly sure, maybe hundreds of watts or tens of watts. So with that, we need a smaller scale device. So we need a smaller scale for macro channel. So it's all relative. So essentially,
I see. I
yeah.
see. I
Uh-huh.
see.
Yeah.
Yeah. Another question always I was wondering is when I was doing some condensation experiments with in the air in the ambient condition, we do notice if we just modified a commercial available like settings with some surface modifications, compare with our homemade surface modification and design, they always win because they definitely the commercial one is definitely optimized like such your work with all this geometry, with all this with arrangements. So I'm wondering like how much the surface modification will play a role in the heat exchangers. Like how, so many people are working on it. There are many like manufacturing allowances, there are many surface design allowances, but I'm just wondering like how much it can impact the, for example, the coefficient of performance.
That's a great question. So I know that yeah, you mentioned for water condensation, those like a natural convection scenario, like for power plant condensers. Those I know that the water if we compare droplet condensation versus film-wise condensation, the heat transfer coefficient is about 5 to 8 times higher for droplet condensation. And yeah, as we all know, and so that essentially is we need to put it in this equation essentially. So how much we increase on the air side, that only plays a role that affect this term, this is the air side heat transfer coefficient, this is the air side area for the heat changer, and this is some efficiency of the some fin efficiency. And my work, as I circled here, my work is more on the refrigerant side, how to recircuitry the condenser using the same material, just like a different allocation of the material, and use the locally higher refrigerant side for locally higher refrigerant flow, make it work with the geometry. So I can say that my PhD work changed both of them. Yeah. So yeah, I guess yeah. It's a I think I'm sure that people for sure have done estimation of like how the surface modification, like for example on the air side, will affect the condenser total UA value or the condenser heat transfer rate value, and then finally eventually the system COP value. But I don't have that number in my mind. Yeah, I only know that yeah, just for heat transfer coefficient is about 5 to 8 times higher. But how it affect on heat changer level and on the system level, yeah, we essentially for to do the estimation on each level, we need a rough model to estimate that. Yeah. But I can say that air side is normally is having larger thermal resistance. So this is essentially a equation for the thermal different thermal resistance. So air side has a larger thermal resistance compared with the refrigerant side. So the impact can be dramatic. Yeah, if you can keep having this 5 to 8 times higher air side heat transfer, yeah, the condenser capacity may be increased by like 2 to 3 times. Yeah, or yeah. So that can be really cause a dramatic change to the system in the end.
Sounds good. That make a lot of sense. And thanks for help me reviewing my heat transfer course. Yeah. Any other people has questions? I'll give it like a 5 seconds pause. If not, let's thank our today's speaker again. Thanks, Jane, for joining us and give this very inspiring and very industrial relevance, very real demonstration of your work. Thanks a lot.
Thank you so much for having me. It is my pleasure.
Yes, thank you. So this is the end of this season 4 of EASF webinars. And we thank all the speakers that has been participating or giving speeches. And also we thank all the organizers that putting a lot of hard works to organizing this this webinar. And thank you all for all the audience to joining us and asking questions and participating and supporting us. So that's all for this season. And thank you all. Have a very good Sunday. And we may see you soon in the next season. Thank you.
Thank you.